All right. Sounds like a lot of you want to listen to me talk for 45 minutes about proxies. This is one thing I appreciate about conferences in Germany. Everybody's on time. I was in Jordan this weekend. I had to start my talk 45 minutes late, which was the duration of my actual talk. Hi, everyone. Thanks for coming. My name is Abdel. I'm a cloud developer advocate at Google. And we're going to be talking about proxies today. And I'm going to start with a very bold statement. And then at the end, I think most of you would agree with me. Everything we use is a proxy. If it's not proxy, it's a VPN. So disclaimers. The content of this talk is actually not what my company pays me to do. This is just me nerding out for 45 minutes. We had a conversation. I was in a conference last year. I was chatting to some people. We had a very interesting conversation. And I went down the rabbit hole for 6 months trying to understand what proxies are. And came out of the rabbit hole with a talk like this. So the content is new. And I would be very open to feedback if you have anything that you think I missed or anything you thought I made mistakes. I'm very open. Just let me know. But basically, if you're a developer, probably this is going to be just fun to watch, but none of the knowledge I'm going to share today will be useful for you day to day. Probably some of it will be. We'll see. Maybe you will do like me and start writing proxies in Rust. So we'll see how that goes, right? It started back in July last year in a conference called JCrete. It's an AND conference in the island of Crete in Greece, where I was talking to Andre and Mary from Oracle and Oleg from Test Containers, now Docker. And Oleg was explaining to me how stay away. Oleg was explaining to me how test containers work and how test containers cloud work. And basically he was saying, okay, well, you run your tests locally, and then you run it against test containers cloud, and in the test containers cloud, we spin up a container that contains whatever piece of software you need to test against. So I was like, okay, so there is a tunnel somewhere. There is a proxy, right? There is like, you're clearly not spinning up a Docker container remotely and exposing it to the internet. So there is something on the client side which proxies connections through a tunnel to get to test containers cloud. And they're like, no, it doesn't. There is no proxy. I was like, how do you do this without a proxy? There has to be a proxy somewhere. And Andres basically made this joke, which is, if it looks like a duck, swims like a duck, quacks like a duck, it's a duck, right? So I tweeted this out, which is, if it looks like a duck, swims like a duck, quacks like a duck, it's a proxy. I thought it's funny. It doesn't have to be funny for you. But the whole point here is, this is how it started, right? And 6 months later, I came up with these definitions. My definition of a proxy, it's a component that sits between a client and server on the network side, and doesn't have to, but it can modify both requests and responses. It doesn't have to always sit on the response side. I'm going to actually show you later. There is a thing in the proxy world where you can make the server return a response directly to the client without going through the proxy on the way out. And then with that definition in mind, what is API management, or what is an API gateway? So API management itself is managing the API. So API is like whatever you build, so other people doesn't need to know how the implementation detail of your backend is. That's the contract you expose. So the API gateway is just a proxy that sits between the API and the clients and can enforce certain policies like authorization, authentication, rate limiting, etc., etc. So an API gateway is essentially just a proxy that knows how the API works. And a service mesh, which we're going to talk about today, is a control point plane for proxies, right? And you can see that I highlighted basically the keywords, but you will, if you read this later on your own, pretty much everything contains a proxy somehow, right? So let's see how can we build a very simple proxy in Rust. I am not a Rust developer. I am learning. So I just went on the internet, and like any good developer, I just write a proxy in Rust and came up with this code, right? I'm not going to spend a lot of time explaining it, but basically what we do is we start a server that listens on localhost port 8100, right? And then to handle the connections, which is this function here called proxy, I am proxying the requests to localhost port 8000, right? So it's a simple proxy that listens on port 8100 and then talks back to something behind it which listens on port 8000, right? So if I go here and I start this app, It will start in a second. Okay, it's listening on this port. So if I take this URL, go to a different tab, and I do a curl, I get an empty reply from server. So there is actually a proxy. My connection was handled by something, but that something didn't know it didn't return anything. So my curl is complaining I didn't get a response from the server, right? I can actually even maybe load it somewhere on the browser so we can look at it. So yeah, but this is actually a valid answer. This means my proxy is working, right? What I could do is I could go and start Nginx. I have Nginx here deployed. I think I am in, yeah. So I just deployed in Nginx like regular, the way you would deploy Nginx. And I configured it. If you have configured Nginx before, you know that the configuration for Nginx is just a text file. I basically configured the server to listen on port 8000 on both IPv4 and IPv6. And this is just HTTP, not HTTPS. So if I just type Nginx. Sorry, I need to sudo. That's it, I have Nginx running. So if I go and curl localhost on port 8000, I get a response from my Nginx server, right? So now, remember that before I started my proxy, which receives connections on port 8100 and proxies back to localhost on port 8000. And I just started Nginx on port 8000. So now what I could do is I could curl to my actual proxy, and I should expect that Nginx will answer me, right? Because it will proxy connections from one port and then forward them to another port, which is what I expected, right? So basically what I did here is I wrote a very stupid proxy that listens on one side on one port and then replay the connections. The technical term we use is proxy connections to a different port, right? Very simple. This is like the most basic form of a proxy. It's just a process that runs somewhere, listens on one port, forwards to a different port, listens on one URL, forwards to a different URL. In proxy world, we call those upstream and downstream. So downstream is essentially the definition. The downstream describes how clients connect to the proxy, and upstream describes how the proxy itself connects to the target server, right? So downstream is the part of the proxy which you talk to, and then upstream is the proxy itself connecting to whatever is behind it. Go back to my presentation for 1 second. So if you have something that sits in the middle of an HTTP request or a gRPC request or a TCP request, it means that basically you're able to inspect the request, you're able to look at the packets, right? By the way, most proxies most of them handle HTTP, and if a proxy handles HTTPS, it means basically that the proxy itself does SSL termination. Because you cannot write a proxy that handles HTTPS requests and forward to another HTTPS server and expect it to inspect the request itself, because the traffic is encrypted, right? In order for a proxy to be able to handle the content of an HTTP request, it has to remove the SSL part of the request. Does this make sense? Right? So it can do a lot of things. It can do authentication. Typically, a proxy can do authentication. It checks HTTP headers and do authentication. It can do authorization because it knows the request itself, like get, put, delete, whatever. It knows the path. It knows the resource you're trying to connect to, and it probably knows also the payload. It can enforce quotas. A lot of proxies, what they do is that they keep an in-memory map of clients, and clients are usually identified by IP address, right? And then for each request they get, they just update a counter that says this IP address connected this number of times. This is the most stupid basic way of doing it. Normally, what they do is that they do it over a period of time, so they will like sample, because quotas in APIs or quota management typically means you are limiting a certain number of requests per a time frame. Let's say 2 requests per second, or 3 requests per second, or 10 requests per minute, or something like that, right? So they keep a memory, but also there is a window of time that the proxy have to keep track of, right? So there is a map that says clients, number of requests, but there is also some sort of timeline that tells the proxy for this particular client over a period of a window of 1 minute or 10 minutes, how many times it tried to connect. And it can do a lot of other things. Like because the proxy can basically look at requests internally, it can do header manipulation. You can actually make a proxy change headers, for example, on the spot. And I'm going to show you a very good example later of how useful is header manipulation in proxies can be. It can block or allow requests based on IP addresses. Like if you are using something like Cloudflare, if you're protecting your websites with Cloudflare and you go on that website on your Cloudflare configuration, and then you go, okay, block US, for example, that's usually what they do. They have a database of IP addresses, so they know the IP is coming from the US and they can block it. And usually they block it at the front end side, at the proxy side. There are, generally speaking, two types of proxies you can find. There are TCP TLS, so those are layer 4. I'm probably taking some of you back to university time. You remember the Aussie model, layer 1 to 7. So layer 4 is TCP UDP, right? So those are proxies that are able to handle TCP, UDP, or TLS requests. And there is HTTP1, HTTP2, and gRPC, and those usually we refer to them as layer 7, right? What does actually mean is essentially, is the proxy able to read the HTTP headers or not? If it's able to do so, then it can handle layer 7 connections. If it's not, then it's only able to handle layer 4 connections, right? Proxies are usually built to be simple and efficient. I think you probably have heard this many times before, but a lot of big companies that handles thousands and thousands of requests. I'm not going to talk about Google Cloud, but let's take an example. In Netflix, they have their own proxy. They had to write their own thing. They cannot use an existing off-the-shelf open source proxy. So a lot of these companies that have to handle thousands and thousands and millions of requests, usually they just write their own thing because they want it to be as efficient and as simple. And a lot of times why they do this, the reason they do this is because they don't want to use a proxy that handles all use cases they don't need. So they will build something specific for the use cases they have, right? It's the concept of the less code you run, the better it is, generally speaking, from a security point of view. So the less code your proxy have, the better it is to secure. And sometimes what happens is you can find some proxies that are able to handle very basic layer 4 or layer 7 kind of connections. But in order to implement more advanced use cases, they will rely on like an external entity. The very simple example is a proxy that talks to an external IDP, identity provider. So it will receive the request. It will look at the user and maybe the JOT token, but it will not validate the JOT token. It will talk to an external server and say, is this thing valid or not, right? So the proxy itself handles the very basic connections, and then it will rely on an external entity to handle more complex connections. And I'm going to talk about a very, very specific example in a bit. These are just some of the very popular open source proxies that have been existed for a while. You're probably all familiar with Nginx, HAProxy, and Apache. If you are familiar with Apache, it probably means you're old, like me. Traffic and Ngrok kind of popped up during this cloud native space, so during the last couple of years when Kubernetes became popular. Traffic and Ngrok were both built actually to be Kubernetes-based proxies. And then all the other proxies now also support in deploying them on top of Kubernetes. So they had to like adjust because there is demand for that. So in a nutshell, to resume, a proxy is an entity that sits between you and your target. Your target doesn't always have to be on the internet. The example I showed earlier, both my client and my target were local, right? It will receive a connection from the client. It will do something with that connection, and then proxy that connection back to the remote server, and then maybe also do things to the connections on the way back, so the response, right? And so you're probably familiar with the term reverse proxy, right? But what is a forward proxy? What's the difference between a forward proxy and a reverse proxy? Well, it's literally where do you situate yourself vis-a-vis the proxy itself. If the proxy is on the client side, we call that a forward proxy. If it's on the server side, we call that a reverse proxy, right? It's as simple as that. So if you're using something like Tailscale, do you folks know what Tailscale is? No? You know what WireGuard is? Okay. For those of you who doesn't know what WireGuard is, you can think about it as a point-to-point VPN, right? So if you are using VPN, you're typically, you have one tunnel between you and the server, right, which is the VPN server. And then in order to access resources behind the VPN server, you have to have the tunnel to the server itself first. And then from there, you connect to whatever is behind it. WireGuard is a protocol that was created such a way that you can create point-to-point VPN tunnel between all your devices. So I can talk about how I use it. So Tailscale is a commercial product, but it's based on WireGuard, which is open source, right? So WireGuard is the actual protocol, and it has implementations in a couple of programming languages. And then Tailscale is a company that took WireGuard and then commercialized it. It's free for up to certain devices. So the way I use it is I have all my devices with the Tailscale clients, and I have also a server at home which has a Tailscale client. And Tailscale itself operates a backend. And that backend, the only thing it does is distribute certificates, because it's based on certificate. The connections are based on certificates. So each time a client wants to connect somewhere, it talks to a Tailscale server, and the Tailscale server tells it, for this specific account, these are the devices which are already connected, and these are the certificates for each of these devices. And then the client will just establish one VPN tunnel to every single device. And then you have a sort of like a mesh of VPN tunnels between all your devices, right? So Tailscale is technically a forward proxy. The client that you have on your laptop is a forward proxy because it's installed on the user side, and then it talks to the internet to talk to some server. Except in the case of Tailscale, that server is just another device, another client. Make sense? All right. So one of the most common use cases for reverse proxies are load balancers. So load balancers are just reverse proxies, right? They sit on the server side, and then they expose one port, one IP, or maybe multiple IPs, multiple ports. Typically, they expose host names, right? Like no one is using 253.68 point whatever to expose their website. It's usually www.mywebsite.com. And so the load balancer itself knows that the IP address it has combined with the host name, it will accept connections on those, and then it will have a configuration to tell it, if I'm trying to connect to /API, forward it to this server. I'm trying to connect to /login, forward to this other server, etc., etc. Make sense? So basically, reverse proxies is just a fancy term to say load balancer. And so a few years ago, there was something introduced to load balancers called DSR, direct server response. So what DSR is, it's essentially a process or a configuration where the server returns the connection back to the server returns the response back to the client directly, right? This is not a genius. This is not rocket science. The way it works essentially is that I'm gonna take one step back here. So let's talk about IP addresses. If you have a load balancer, we have a client and we have a bunch of servers. We will have an IP address on the client side, right? We will have an IP address on the downstream part of the actual load balancer itself, right? So that's the IP address that the load balancer exposes to the world. Then the load balancer will also have an IP address here that it will use to connect to the servers, right, for the backend. And then each server will have its own IP address, right? So typically the way connections work is that the client connects to the load balancer. The load balancer terminates that connection and starts a new one toward the backends. And then in the memory of the load balancer, it knows that for this particular client, this is its IP address. So when the load balancer is forwarding the request, it will forward it with as a source its own IP address. It will not use the client IP address to forward the response. So the response, when it goes back from the server, it goes back to the load balancer and then back to the client. This is when you don't have DSR enabled. But if you do DSR, you essentially what you do is you keep the client IP in the request and you forward that to the server. So the server, when it wants to respond, instead of responding back to the load balancer, it just responds back to the client directly. Make sense? This is actually implemented in a lot of, all modern proxies implement this kind of implementation because it's just more efficient. It's just one less stop on the way back on the response path. Make sense? Right? So what about gateways or API gateways? So a lot of times people talk about gateways, and like in all the research I have done, I really could not find anything that would distinguish a gateway from a proxy. It's just a generic term that says a proxy, right? Usually people, when they say gateway, they usually means like an endpoint, like somewhere you connect to, right? Gateway, the term itself, sometimes is even used in, the banking system, a payment gateway, for example, if you're working with banking systems, which basically means a remote server that you connect to process a payment, right? But for the purpose of simplification, whenever people say gateway, just think proxy, right? That's it. It's very simple. Gateways can do load balancer, can do authentication, can do authorization. They can do everything a proxy can do, right? API gateways particularly are special type of proxies. So they're proxies but they kind of know how the API works, or they know the logic of the API. So they know the endpoints, they know the methods, they know what's exposed to the client, and they have the logic to forward the requests back to whatever backend is behind the API gateway. And they can have all the functionalities that we talked about that proxies have. So rate limiting, authentication, authorization, all that stuff, right? So yeah, so that's basically how API gateway usually works. It just sits between you and the client, has a bunch of backends, and typically on the front side or the downstream side of the API gateway, the API itself is stable, doesn't change, or if you change the API, you have to publish like a schema change, so or you version the API, so you tell people there is a new version which has different parameters and different methods. And then on the upstream side, it's just whatever backend is behind the gateway. And as I said, they come with features. So SSL offloading is a very typical feature in API gateways. Response caching is another one. Login is another one. Routing, that's very typical. Authentication, authorization. You remember earlier when I said the proxies can sometimes rely on external entities to do certain implementations. This is just an example, which is authentication. So the API gateway itself doesn't have the logic for authentication. It just receives a request, and in the request there is the identity, and then it just sends that identity up to an identity provider to say, hey, is this identity valid or not? Is this JOT token valid or not, right? And now let's start with confusing terms. The Kubernetes community introduced a new API in Kubernetes, and they called it the Gateway API. It is completely different than API gateways. It is actually not an API gateway. It's far away from an API gateway. It's as far away from an API gateway as things can be, right? So I'm going to deep dive a little bit here to explain what the Gateway API in Kubernetes context is, and then we'll go back to proxies. Surprise, surprise, there is still a proxy somewhere, right? Remember when I said at the beginning there is always a proxy? Or everything is a proxy? There will be proxies showing up here. So back in the days when Kubernetes itself was created, 10 years ago, they needed a way to be able to deploy applications into Kubernetes and expose them to the internet, right? So they created something called Nginx. So in Kubernetes space, if you're talking about Nginx, you have to distinguish Nginx with capital I or Nginx with small I. Nginx with small I is the pattern, is traffic coming from outside to inside, right? And the opposite of Nginx is egress, good. Ingress with a capital I is an actual API. And the way this API works is that you, as a user of Kubernetes, you create an ingress object, and then there is something that will deploy a load balancer for you. And that something is typically a controller, right? It's an ingress controller. The controller pattern is something that exists in Kubernetes since its creation, but I'm not going to go into details. You can think about it as a piece of code that you tell it to deploy something, and it deploys it for you, right? There are a lot of ingress controllers, actually. All the proxies I talked about earlier have their own implementation of ingress controllers, right? So Nginx, Traffic, HAProxy, all of them. And then there is sometimes cloud providers have their own implementations of the ingress controllers, because a lot of cloud providers have their own load balancers, which are usually distributed. So they write a custom ingress controller that integrates the ingress object in Kubernetes with whatever they have in their infrastructure. Make sense? So actually, a lot of times, if you deploy Kubernetes yourself and deploy one of those 3 top proxies, which are the open source ones, then you are deploying technically 3 things. You deploy an ingress controller, right? Which is the component that knows how to configure the proxy itself with whatever configuration you want. It deploys the proxy itself. So there is still a pod running somewhere which acts as the proxy. The connection goes to the pod first, and then they get forwarded to your backend. So that's the load balancer itself. And the third thing is a CRD. I'm not going to go into the details. You don't need to understand what a CRD is. So typically, as a user, this is what you do. You write a file called ingress, a YAML file, right? Kubernetes is YAML-based programming. You give it a name, and then you give it some specs. So this is an example where we say we have a TLS host. A TLS host just basically means HTTPS. It's encrypted. The host itself is cafe.example.com. This is where the SSL certificates is. Just a secret. And then I go, for this host, whenever people try to connect to /t, you send them to this backend. And if they're trying to connect to /coffee, you send them to this backend. Right? This is just load balancer, right? You're just saying, and typically sometimes you even have a way here to define a fixed IP address, because for load balancers you want a static IP address, right? Make sense? And typically that's the IP address that this host resolves to. So cafe.example.com will resolve to whatever IP address you have. So that IP address we define in the ingress object is the downstream side of the proxy, right? So that's what the proxy listens to. And then the upstream part is the backend here. Here we have two backends with two different paths. Make sense? So ingress existed in Kubernetes since its inception. Not really since its inception. I think it came in 2015. Kubernetes came out in 2014, but it doesn't matter. It actually was very, very widely adopted because it was the only way you could define external load balancers in Kubernetes world, right? You couldn't do it any other way. It has enabled an entire ecosystem of people implementing all sorts of controllers. So these three implementations I showed you here, these are just like a subset of the example. I think last time I checked, there is about 80 implementations of the ingress controller itself. Because the ingress controller implementation is specific to whatever proxy you're using it with, right? So for each of those proxies, there is a specific ingress controller deployed for it. Make sense? Remember, the ingress controller is the component that will take your ingress object as an input and configure the proxy accordingly. So to configure the proxy accordingly, you need to write configuration specific to that proxy, and proxies are not configured the same way. Every proxy has its own configuration. Make sense? Good. So the bad part about ingress is that it was created to solve the lowest common denominator. It was created to solve the basic use cases that all ingress are trying to solve. So what happened over time is people started adding extensions to this object to be able to do something specific that Nginx can do that HAProxy cannot do, or the other way around. And that became too much. Actually, they were implemented through something called annotation, which is just metadata that you add to your object. And it got to a point where in order to deploy something useful, your annotation has like 200 lines, which is not very readable, not very easy to debug. So they introduced this concept of gateway, which is what they call the gateway API, right? So it's a new API, which is supposed to replace ingress. And in it, you have, they tried to solve multiple problems or multiple limitations that the ingress had. One of them is the fact that you can split responsibility between the people that manage your platform and the actual developers. This is just an example. Again, you don't have to, I don't want you to understand this, you don't have to, it's just a very specific implementation detail of ingress of API gateway, but this defines a load balancer, and this tells the load balancer how to forward traffic to a specific backend. And the other thing they solved, which was the crucial thing, is in Kubernetes there is this concept of namespaces. So a namespace is just like a place where you put resources. In ingress, you couldn't actually put the ingress object in one namespace and the backend in a different namespace. They both had to be in the same namespace. The gateway API solved this problem, right? Now you can have your backend, your gateway, your load balancer definition in one namespace and the backends in a different namespace. Anyway, I don't want to spend too much time here, but whenever you hear API gateway and gateway API, these are two different things, right? They kind of look similar, but they solve two different problems. You cannot use the gateway API in Kubernetes to manage an actual API with an open API spec, for example, right? Make sense? Okay, good. I hope we cleared this confusion. So, what have been happening also very recently is there was a lot of these new modern, I call them, proxies that started popping up. And I'm going to only talk about Envoy today because it's the most widely adopted modern proxy. But there is a lot of other implementations. So what is Envoy? So Envoy is a proxy that was created in Lyft. Lyft is the ride-sharing company in the US. We don't have it in Europe, but it's kind of like Uber, right? So they were using HAProxy, I think, and they got to a stage where HAProxy could not solve all their problems. So they wrote a proxy from scratch, and they call it Envoy, and they open sourced it. It's written in C++. And the particularity, so like any proxy, it has upstreams and downstreams, right? So upstreams is essentially defines what port and an IP address the proxy itself listens to. And then downstreams, they call them listeners, and that basically tells it what backend to forward traffic to. So this is just go to this, whatever you could receive connections on the port on the front end, forward to this backend. So they call those listeners in the context of Envoy. The key difference that Envoy has that the other proxies doesn't is the fact that you can configure it with either a file or with gRPC, right? So you can write a static file the same way you remember the Nginx file I showed you? The same way you write a configuration file and then you point the proxy to the file and then you start the proxy and then it does its things. Or you can use these APIs, they call them XDS. So XDS is just a set of gRPC APIs implemented in the proxy itself. So the proxy has a specific port it listens on and it receives gRPC commands that are XDS formatted and then it can change its configuration, right? So what you could do is you could actually run what we call an XDS server and use that server to distribute changes to a cluster of Envoy proxies. Does that make sense? So it just gRPC commands. I mean, I don't know how to explain it more. it's literally a remote configuration server, right? The proxy talks to the remote configuration server. Whenever there is a configuration change, the proxy will change its behavior. The reason why this is important is because this gives us dynamic configuration, which basically means if we change the configuration, we don't have to restart the proxy. Make sense? All right. Now, what actually Envoy allowed us to do is it created this whole genre of what we call a service mesh. And today, most service mesh implementations exist on the market, most stable ones, and I emphasize stable because there is a lot of new service mesh tools trying to do all sorts of interesting things. But the stable ones are all proxy-based. So let me explain. Let's say that you have two services that need to talk to each other, right? Two applications. They can be talking HTTP, they can be talking TCP, they can be talking gRPC, they can be talking any protocol you want. Let's say you want to add MTLS. You know, anybody knows what MTLS is? What? Yeah, not the definition of MTLS. You do handshaking both ways, essentially. You all know what TLS is, right? It's the server has an identity, and then the client verifies the identity of the server. Mutual TLS, both have client and server, both have identities. In other terms, both of them have a certificate, right? So when the client is initiating a handshake, it sends its own certificate to the server, and the server can verify the identity of the client. And then when it receives a response, the client can verify the identity of the server. And then they both have public keys that they can use to encrypt both traffic in both ways. Make sense? So if you want to add MTLS between two services, it doesn't matter what the services are, by the way. They can be two servers. I mean, you can do it, but the problem is once you get to a point where you start running 100 instances of service A, 100 instances of service B, doing it manually becomes painful, right? For example, what if your certificate leaks and you need to rotate it? Or what if you are changing your certificate authority? Or what if you are doing anything, right? Like handling certificates at scale is not easy. So somebody came up with the idea of why don't we write a control plane and let that control plane handle all this MTLS, TLS, whatever, certificate distribution, rotation, etc. And if we have a control plane, we can also make it do other things. We can make it do policy enforcement. We can take some reporting out of the services, etc., etc. And so because we have a control plane, we need a data plane, right? If you have a control plane, you need a data plane. The data plane in the context of most service mesh implementation is actually a proxy. So essentially what it means is that you have your application, next to it there is a proxy, that proxy talks to a remote configuration server, downloads the configuration, and then it sits between the services. So service A sends its traffic to the proxy does everything that the control plane tells it to do, sends traffic to the other proxy on the other end, then the other proxy does everything that the control plane tells it to do, and then send the traffic down up to the service. Those proxies are actually very transparent, which means that the service, whatever these applications are, they don't even know that there is a proxy. They just know that they connect to a port and it just works, right? So then you can just make the proxy itself, for example, do all the MTLS stuff. So instead of implementing the logic of MTLS, the handshake, encryption, all that stuff, instead of implementing it in the application itself, you implement it in the proxy. Make sense? And that's essentially what Istio is. So Istio is one of the most popular service mesh implementations today on the market. It has a remote control plane called Istio-D. It runs on top of Kubernetes, but that's not very important for our purpose here. Istio-D implements the logic the configuration logic. So that's the remote configuration server, right? And then is2d just distribute the configuration to the proxies, and whenever you need to change something, you change it in is2d, and then is2d knows how to configure the proxies. So if I go back in my slides 1 second, come on. is2d is the XDS server, and then envoy is the proxy that runs next to the applications, right? So you configure XDS, the configuration server, and then this thing knows how to configure the proxies. So that's essentially what a service mesh is. So now I'm going to stop a second, and I know that probably I've been boring you for the last 5 minutes with details. I'll ask you a question. Why do we call it service mesh? Where does mesh come from? Have anybody stopped for 1 second to ask this question before? No? Can anybody give me an answer? Partially. It's very simply because, sorry. If we go back here, if you just have two services talking to each other, right? What you need to do is you need to configure the IP address of service B in service A, right? So that service A knows how to talk to service B, right? Now, if you start running multiple instances for service B, you need something in the middle. So what are you going to use? A proxy, right? The talk is about proxies. So you're going to use a load balancer as a reverse proxy, right? And then you will put a load balancer in front of all the service B instances, and then make service A talk to that proxy, and then the proxy will forward the request to service B. Following with me, right? This means basically that if you have multiple service A and multiple service B, you have an endpoint in the middle, it's a proxy. Good? In service mesh world, those little proxies here, there is one proxy running next to each instance of each service. It's not one proxy per service, it's one proxy per instance. So if you have 100 instances of service A, you will have 100 proxies. And we call it a mesh because the proxies know where all the other proxies are. And that's why we call it a mesh, right? So there is no concept of load balancers. There is no single point. There is no reverse proxy. All these proxies act as both forward and reverse proxy at the same time, right? So any instance from service A trying to talk to any instance from service B, that instance of service A will send the request to the proxy, and the proxy will basically know what's the other end, where to send the request. And it will send the request directly instead of passing by a load balancer. Does that make sense? That's why we call it a mesh, because all the proxies know where all the proxies are. Okay. So last couple of slides, and then I'm done. There is like ingress and there is egress. I'm not going to go into details. What's been happening right now is that there are actually two efforts. So this implementation has a bunch of downsides. One of them, is the fact that those proxies consume resources. Imagine you have an application that has 100 instances. You add service mesh to it. You have 200 instances of you have 100 instances of the application itself, and then 100 instances of the proxy itself. And proxy needs to consume CPU and memory and those stuff, right? And so then it's like difficult to debug and a bunch of other problems. So there are two main efforts to try to solve this problem. One of them is a new architecture in Istio called ambient mesh. And so I'm not gonna, like the very simple example here is think about the purple boxes as nodes. So those are the actual physical nodes, servers, right? The blue rectangle is the cluster, Kubernetes cluster. And then the containers are C1, C2, S1, S2, S3, right? So what ambient mesh does basically, it introduces a new two types of proxies. Thank you. One is called zTunnel. This proxy does all the layer 7 stuff, the MTLS things, all the basic things, the security stuff. So this proxy here runs on the node. There is no more proxy next to each instance. There is one proxy for the entire node. All the connectivities from these containers or applications go through this one single proxy, and then they get routed to the proxy on the other end. And if you need layer 7, so if you need to do authorization, if you need anything that knows how to handle layer 7 stuff, you deploy something called the waypoint proxy, which is shared per namespace in the Kubernetes world. Again, too much details. I'm going to skip it. I just wanted to show it. But basically, between this and this, the key thing is reducing the number of proxies, right? In Kubernetes space, those proxies, they call them sidecars. And this is why sometimes if you go to search for this topic, you will find that ambient mesh is sidecar-less implementation, because there is no more concept of sidecar, technically. But again, maybe after you go home, you can Google this stuff. The other implementation is eBPF based. If you don't know what eBPF is, you can think about it as Spring Boot inside the kernel. It's a framework that allows you to program the kernel without having to write code in the kernel itself. It runs in user space. And so Cilium is another company, or product technically, that actually is trying to take all the stuff that Envoy used to do as a sidecar and then replace them with eBPF, right? So it's just two different approaches to try to solve the same problem, reducing the number of proxies on the nodes, on the cluster generally speaking, by either implementing it with eBPF or with the ambient mesh, which is what I showed earlier. And with that, in a nutshell, if you take anything from this, everything is a proxy. Thank you. Was it too boring? All right. Was it nerdy? OK, that's what I wanted. I think we have 4 minutes for questions. Yeah. Any questions?
I have a question.
Mm-hmm.
So is API gateway always a reverse proxy, as it's so much?
Yes. The question is an API gateway always a reverse proxy? Yes. Because it always sits on the server side. You never deploy the API gateway on the client side. Except so Envoy, they released something called Envoy Mobile, which is actually technically not a proxy, although it works like a proxy. It's a set of libraries that you can implement in mobile applications on the client side. And you can make it do a lot of things that a reverse proxy typically do. But that's the only implementation which is closer to an API gateway on the client side that I'm aware of. OK? No worries. Yes? To rewrite the context path? Yes, yes. That's actually a very common implementation. Because a lot of times, so sometimes what happens is that you, I can actually give you a very concrete example, right? The podcast I co-host, we used to deploy, so the website itself is just a static website deployed in a blob store. We use Google Cloud Storage, but I mean S3 or Azure Store or whatever, it doesn't matter, right? So we have a bucket, and then we put load balancer in front of the bucket, and the requests go to the bucket, and then they are served to the load balancer, and then we serve from the bucket, right? We used to host our MP3 files in that bucket, right? At some point, we moved to use a third-party solution, and that third-party solution gave us analytics. So the key question we had was, how can we forward the feed? Because you know how the way podcasts work is that there is a feed, an RSS feed, that you, as the publisher, you update each time you publish a new episode, and that's what clients like Spotify, Google Podcasts doesn't exist anymore, but like, you know, podcast clients, they read the feed, right? So because we already had people subscribe to our podcast, we could not expect them to just change the feed, right? So how do we do it? Well, we basically just took the existing path and forwarded it to the new feed hosted by the third-party provider, right? So now we have a third-party website. We host the MP3 files there. They update the feed for us, but the existing users, they just talk to the old path of the feed, and then we forward them to a different path. So that's an URL rewrite, essentially. Does this make sense? And this happens a lot. So if you rely on a third-party company, and then that third-party company changes their IP address, how do you do it? Like, you cannot expect the clients to update their URLs, right? So you just keep your clients pointed to your existing load balancer with your existing path, and then you can rewrite the path to a different location. Yes?
My question is about DSR.
Yes.
I see this picture you showed already, and some questions coming up in my head. So is it secure really? So if you get the internal IP on the client side, is it secure, or which cases can be applied this kind of technology?
You mean on the response path, you have the IP of the actual server that responded, right? Well, is it? Because normally, if you have a load balancer, the servers behind it are private. So even if you leak that IP address, it's private. No one can connect to it.
Okay, so it's not reachable, right?
It's no, typically in an implementation, I mean, in any implementation where you have a load balancer, normally your servers are private, like the backends are not, they don't have a public IP. Because if the servers themselves have a public IP, there's no point of having a load balancer, right? So then in this case, yes, on the return path, the packets that the client will receive as a response will have as a source IP the server that respond to it. But that IP address is private, so it doesn't matter. It cannot be reached from outside. Make sense? But there are actually techniques where you can avoid that. Because, I mean, you could technically just, because the point is that no, sorry. What you could do actually is you could make the server, instead of responding with the source IP, its own IP, it would respond with the source IP, the IP of the load balancer. Right? So that the client will receive the packet as a response, and it will see, okay, the source is the IP address of the load balancer. So the client doesn't even know that this was the server responding to it. It thinks that the load balancer responded. I mean, it's packets. You can write whatever you want in packets, right? Make sense? All right, any other questions? I think, yes, last question.
One of the slides is HTTP route and API gateway client Kubernetes.
Yeah.
And we have already explained the ingress problem. Does it mean we should not use ingress anymore and shift to this API gateway HTTP route?
So if you have to go look into the implementation, because the gateway API is still in the making. So the question is like, should you replace the ingress with the gateway API? The gateway API is still in the making, and not all the APIs inside are actually GA. Some of them are still beta. So if in the existing, if in whatever is GA now, you find the use cases you find, like you can use it, I would recommend you to use it. Because eventually the ingress will be sunset. I'm not talking about now. I'm talking about maybe a few years, 5 years, maybe 6 years. But that's the goal going further, is at some point ingress will be sunset. Make sense? All right. Thank you very much. I hope this was useful.